Let's try this question. A spherical concave shaving mirror has a radius of curvature of 32 cm. So I have a concave shaving mirror. So let's try and draw a concave mirror. Concave mirror should probably look something like this. Then it has a radius of curvature of 32 cm. So the circle will be around here. So the radius should be in front of the mirror itself. So if you draw you can say this is the center of curvature. We'll just do a rough representation to let us see how things work. Okay, then we can label the distance here to be 32 cm. 32 usually just convert into meter. It's just a habit of mine. Okay, 0.32 meter. Okay, then the next sentence, what do they say? What is the magnification of the person's face when it is 12 cm to the left of the vertex of the mirror? So 12 cm to the left of the vertex. To the left of the vertex by 12 cm should be somewhere around here, I believe. Okay, so if you measure here, then you come up with 0.12 meter. Then this is where your person's face, in this case, since it's a shaving mirror, your person's face will be the object. So over here you have your object. Object is usually upright. Yes, you don't put things upside down, right? Okay. So this is what we know, the information that we know until now. So they ask for the magnification. Well, magnification, you know just now from previous video, it's either negative v divided by u, the image distance divided by the object distance, or the image height divided by the object height, but without a negative sign. In this case, I believe height is not a concern because we don't even know the size of the face right now. We know the distance of the face from the vertex of the concave mirror. So I think it's better that we focus on the image and object distance. So let's try and figure things out. The image distance we don't know, so we still keep it as v, we still haven't substituted it yet. But the u, the object distance, so to determine the object distance, whether it's positive or negative, again recall, your incoming ray, your incident ray is coming in this direction from the top point of the object towards the mirror. In this case, your incident ray is in front of the mirror, and your object is also in front of the mirror. So both of them in front, so they are the same side. So the object distance should be a positive value. Since it's a positive value, we can straightaway substitute it to be 0.120 or 0.12. So we still don't know v, but since we know the characteristics of the mirror that we have here, if you know the characteristics of a mirror, if you know the characteristics of the object, we can actually find the characteristics of the image using the mirror equation. So mirror equation is 1 over u plus 1 over v equals to 1 over f. So you know just now the u is a positive value, so you can just write in 0.12. If you are being very careful, you can write a positive sign in front just to remind you that every u, v and f should have a positive and negative sign. So plus 1 over v, that's what we want to find out. Then it equals to 1 over f. So we need to find whether this focal length here should be positive or negative. Remember, when we come to focal length, we see the reflected ray, whether it's on the same side or the opposite side to the to the center of curvature. Center of curvature is in front of the mirror. Then our reflected ray will be reflected back towards the left, right? So if it gets reflected back to the left, then we know that the reflected ray will still be in front of the mirror. So the center of curvature and the reflected ray are both in front of the mirror, so they are at the same side. So if they are at the same side, then we know that the focal length will be positive. But we don't actually have the value for focal length. What we have here is actually we have the radius of curvature, which is 32 cm. Okay, suppose the highlighter 32 cm for the radius of curvature. So knowing that, we can actually determine the focal length by using the relationship r is equals to 2f, And since the radius of curvature is at the same side to the reflected ray, then we know that same side should be positive. So radius of curvature, we can substitute in a positive value. So it will be positive 0.32. Okay, you can ignore the 0, put it 0, that's fine at our level. So 2f. So you find that the focal length will be equals to 0.16 meter. Okay, you can add a positive sign, just be very careful with things. Then you can substitute positive of positive 0.16 over here. Then you determine your image distance to be negative 0.480. So what does the negative here tells you? Well, the negative, if you get an answer which is negative, it means opposite side, right? It means that the image is formed at the opposite side to the reflected ray. So if your reflected ray is in front of the mirror, then the image is now formed behind the mirror. So if you have image formed behind the mirror, because you know the ray will not pass through the mirror, it's an opaque object, the ray cannot pass through. So any image that you form behind the mirror will be the intersection of the extension of the reflected ray. It's the extension of the reflected ray that caused the intersection. So because it's an extension, it's not an actual ray, so the image that is formed is actually a virtual image. So that's what the negative V here tells you. Okay, it tells you that it's a virtual image. Okay, so knowing that, we can substitute this 0.48 inside, negative 0.48. Remember to retain the negative sign. Then you find that your magnification will be equals to 4. Okay, magnification has no unit, it's just a ratio. So this magnification equals to 4 here, what does it tell you? Well, since the absolute value of m is greater than 1, it means that it is magnified. Okay, your image will be larger than your object. And also, since your m here is positive, then you know that this should be an upright image. So you know your characteristics of your image will be virtual, upright, magnified. So it will be virtual, then upright, magnified. They didn't ask for it, but they asked for where is the image. As for where is the image? Well, the image is here. Okay, let me highlight it. Okay, they already mentioned that the image will be here, 0.48. But 0.48 is still a measurement. We are still not sure whether the 0.48 is around here or the 0.48 is around here. Okay, we need to know whether it's in front of the mirror or back of the mirror. But since we know that it's negative sign, it's telling us that it's on the opposite side of the reflected ray. The reflected ray is reflected in front, so opposite side will be behind. So it means that your image will be formed behind the mirror. So image formed behind the mirror, something like this. It's magnified, it's upright, so somewhere around here, you have your image, then you label this as I, then yeah. Then you should talk about the where is the image, right? You can say the image is 0.48 meter to the right of the vertex of the mirror. Use the sentence in the question. To the right of the vertex of the mirror. Okay, so you have answered the question here. Where is the image? Then is the image virtual or real? The image is virtual. So you have successfully answered A and B. Then now if you move on to C, draw a principal ray diagram to show the formation of the image. Well, we have been doing that for quite a while, so I will just brush through it. Okay, so the principal ray should consist of minimum 2 rays. Minimum 2 rays. So I've introduced 3 rays, right? If possible, if the situation is possible, draw all 3 of them. Only if it's impossible, then you draw 2. So here I have tried to draw the image, draw the ray diagram. So you can see here that the brown ray should be usually the first ray, which is parallel to the optic axis, then get reflected towards the focal point. Then the next one will be the incident ray will be along the line that passed through the focal point. It strikes the mirror, then get reflected parallel to the optic axis. Then the last one will be the incident ray that is along the line that passed through the center of curvature. And we know that the reflected ray will be just along the same line, just in the opposite direction. Okay, so you have these all three rays here, and if you extend the ray backwards, the reflected ray backwards, you see that they intersect at a specific point here, which is behind the mirror. So therefore, you are able to prove that this image here should be a virtual image, and in this case, since it's larger, it's magnified, and it's on the same side of the optic axis, means by it's upright. So virtual, upright, magnified. Okay, so something to notice here is that the ray, I only label the arrow for solid rays. Okay, I don't label it for the dotted lines, because dotted lines are just extension of the line only. But there's also another dotted line here. The dotted line here is just to show that this ray that is incidenting on the mirror, if you extend it, it will be along the focal point. Okay, this is not an actual ray, this is just to show that the direction of this incident ray is along the line that passed through the focal point. It's not an actual ray, it's just to show the direction is along this line and pass through the focal point. Okay, so this is how you draw the principal ray diagram to show the formation of the image. Of course, if you see here, the arrow here and the arrow here is only about twice the size, right? But we learned from the previous working that the magnification is 4. So that shows the flaw of using ray diagram, because everything is approximate, right? You can't really, you know the relationship will be magnified, but the diagram, if you don't draw it really precisely, really accurately, you are not able to show that the image will be 4 times the length of the arrow compared to the image. And that's the flaw of ray diagram that requires us to use the mirror equation and magnification. Okay, so that's all for this question.